He will not force the weakness to be out.
Before we start a general discussion, are there any sort of burning questions that came up in people's minds as a result of both, well, all presentations? Yeah, David.
I'll use my position. Yeah. So, John, you use star formation, like maximizing the number of stars from baryons, as sort of a proxy for observers, right? You used it as a proxy for making us, and you said what we want to do is maximize the baryons turning into stars so that you get the most people, and that's sort of the private application there. But from Adrianne's talk, it seems like you want to sort of maximize stars in a galactic bulge, which might not necessarily be inhabitable, right? So how good of a proxy, I want us to get at, how good of a proxy is this for observers or cosmologists?
Well, let's break it down. Obviously, that proxy is only appropriate for a particular simplified situation, which is where you're imagining an ensemble where you don't mess around with the baryon content of the universe. Mm-hmm. So then, it's the simplest imaginable case. But let's say I've got two copies of the universe, right? Funding is short. And they're identical in all respects. They contain, they have they're large, but let's assume that they are finite in terms of their total mass. So they contain some amount of baryons, and so I think if you have one where the fraction of those baryons that turn to stars is 10 times as large as the other, I'm willing to say I'm 10 times as likely to live in the one where the efficiency is high. So I think that's okay at an order of magnitude level. There's all sorts of things you can quibble about about factors of 2, because what you're really after is down at the planetary level. So you want to know, well, okay, what's the probability of a star forming planets, and what's the probability of those planets being in the habitable zone, da-da-da-da. But when you've got many powers of 10 to argue about before you get down to that.
So if I understood correctly, the way you interpreted what I was saying was that you want a bulge because you want to have a stable disk, so that you could have
within that you can have observers and so forth.
Exactly. But there are other ways. So part of what makes the galaxy, a disk galaxy, be unstable is the high surface density. So the stuff I was showing you was high redshift. And so if you run that simulation lower, eventually you will deplete the gas from, some of it will be turned into stars, right? And eventually, even without a bulge, you can get a stable disk. So having a bulge is not the only way to get a stable disk.
But so I don't get the point about worrying about stability.
So
I thought in the simulations, even with without the bulge, we still get roughly the same fraction in the end of stars as within a factor of a couple.
Yes.
So if David's argument was just having a bulge gets you more stars, that's actually not what we see in the simulations. So it's not what's needed.
Well, I mean, my point is more a case of how much of stability is needed for the production of observers. If we have a lot of stars made, but perhaps, I don't know, they're spread out or they're colliding with one another at great rates, or you're in a high density radiation region, you wouldn't necessarily be able to use number of stars as proxy for number of observers. I was just wondering if maximizing number of stars in one instance is actually limited by other factors.
But I mean, what's the habitable zone in the Milky Way? If you pick the sun up and put it in another part of another location and even another part of phase space, I mean, the stellar system's pretty nearly collisionless, so you don't have to worry about running into other stars unless you're right down near the central black hole.
You don't want to be too near a supernova or too near an AGN, but the supernova, you can't do anything about. The AGN just means the habitable zone's an annulus.
Yeah, but it's small.
It's probably a couple of kiloparsecs, something like that. But it's not. I don't think it's a major problem, actually.
But it seems that in order to kick off star formation, you need to overcome the critical density.
Mm-hmm.
But as soon as star formation is ongoing, it seems that all disks settle around this critical density. They come back and star formation carries on steady state along this critical density. So is there an indication how this process happened, or because chemical data that you showed, so almost all galaxies evolve along the critical density.
Right. I mean, of course, I know you know this, right? The density in the galaxy is not uniform. You know, once it's forming stars, right, there will be regions in the galaxy which exceed some critical density. But there's a variation. So whether a galaxy is star forming or not has to do with how many regions it has that exceeds a critical density. So I don't really see.
Yeah, critical density change along the galaxy.
Right.
But locally, at every region,
Right.
every region in the galaxy, the density of the gas, star formation still evolve, just always along this
Right,
marginal
I see what
line
you're
of
saying.
stability.
Right.
So that's
Right.
and that seems kind of fantastic. That
Yes.
It happens this way, that the whole misty dynamics, it pushes the galaxy to settle along this line of stability.
Right. Yeah. I don't think it's well understood.
If I want to speculate, John, we know that our universe is settled along the critical density of the universe.
Yeah, yes.
But at the same time, the same process happens in galaxies. So is this an indication that there is some universal process that is acting on large scales and local scale of galaxy?
Well, I doubt it. I mean, the fact that the universe is of zero curvature, that's a geometrical statement. It doesn't change with time. So you set the density to the critical value at one time, it's there. It has to occupy the critical value at all subsequent times. Okay, and it can't evolve towards it. I mean, the universe, if it's curved, it's either positive or negative curvature, and there's no means of mapping from one to the other. So I can't see that's a valid analogy.
Okay, if there is a kind of process that is scaled, can be scaled, like fractal process that is operating at the level of the universe, where the evolution of the universe, as we see it now, is settled around the critical density. This is the observations on the show. And we see the same phenomenon happening at the level of galaxies. At the scale of galaxies, the same process is happening. There is critical density along which the galaxies evolve as well.
Yeah, but those processes are completely
They're
different
completely
physically.
different,
aren't
but
they?
Yes,
we
So
have scale.
they're independent.
I mean, if you wanted to press that analogy, I suppose you could say that, well, obviously we don't know observationally what's happening beyond a current Hubble radius. So on a large enough scale, the universe could be highly heterogeneous, and so different domains within it could have different properties, and so it's settled down in one region to a particular value. But in a sense, that's what inflation does.
Yeah.
Inflation says the universe is very, very much larger than we currently observe, and it emerged out of something that wasn't necessarily spatially flat, but was driven towards it. But anyway, I mean, once it's there, it's stuck, which in principle is not the case with galaxies.
Mm-hmm.
So,
I wanted to ask Adrian a question. This is a bit out of my field, but my understanding is that we have supersonic strong turbulence, and that's producing density fluctuations. And in the regions of high density, then of course we get above the density critical, and we initiate star formation. What's the time scale of these fluctuations compared to the time it takes to build a star?
Right. I don't know.
Does the question make sense?
Yes, it
These
did make
fluctuations
sense.
have a characteristic time
Right.
scale, and presumably
Right.
the stronger the turbulence, and hence the closer towards
Right.
critical density they are, the shorter the time scale comes.
Right. No, so you're thinking, so that's the kind of measurement so this idea is, for the galaxy formation simulations, is motivated by people doing these simple simulations of, boxes of turbulent gas, okay, where they start off with, uniform density and no velocity, and then they shake it with some turbulence, okay? And the question you're asking is something that we could start to answer, I think, in a simulation where you have the PDF changes depending on where you are in the galaxy.
Basically, you've frozen the turbulence.
No, it's dictated by the dynamics of the galaxy, right? That galaxy is growing. You saw in this complicated web, right? In this cosmological web, and it accretes gas. It's spinning.
But that means that you're predicting the turbulence will decline, so it won't be continuously regenerated in the future when that accretion switches off.
Possibly, perhaps.
Isn't
But
it
there's still rotation.
I was going to say, isn't it mostly generated by differential rotation?
Right, exactly.
Supernova too, another
Supernovae,
Yeah.
yeah. So it's an interesting question. What happens?
So
when-
secular processes, like differential
Exactly.
rotation can drive
Exactly. A
turbulence,
bar.
which wouldn't necessarily mean it would fall over
Right.
cosmic time.
Right. No, but your question is an interesting one. So we haven't looked at that, the time scale.
I just ever wonder whether the turbulence is of such a short time scale that it's the fluctuations kind of faded away before the stars grow.
Right. So it requires the turbulence to be sustained long enough to
Yes,
form
exactly.
stars.
Well, presumably when the density gets large enough, then gravity can take over.
Right.
So if it's just turbulence, it's just sound waves passing
Exactly.
through each other. But
Yes.
gravity can kind of cause it to
That's
stick,
certainly
surely.
true. Gravity's always on our side, isn't it? Thank you.
Does anybody else have a question on this kind of area? So maybe we should switch areas. I don't know whether anybody has a new topic they want to ask about. I have one or two ideas, or whether the
By the way,
speakers want to raise anything.
if there's any questions for Joe, you have to answer.
Yes, I had that in mind. So I would let me start off an idea. So my sense of your talk really was that you recognise that you showed us that there's a lot of progress in this area, but there are also a lot of areas of ignorance, and this is all
Yes.
to do with the dynamic range of the simulations
Yes.
and not knowing the microphysics.
Yeah.
But the sense in which the impression with which you left us appropriately is that this level of ignorance is merely our inability to understand and model the physics. But your assumption is that the underlying physics is there and understandable and modelable. So if you had in principle an infinitely large computer, you would be able to form the sun and all the stars around it and so on. Right? That's your approach.
Well, I wouldn't say that the physics is all. No.
No, but in principle, the physics is solvable, right? So there's no.
But what does that mean, Roger? I mean, you might as well say brain surgery is just solving Schrodinger's equation. I mean, we're never going to. That's never going to be practically useful.
No, but in contrast to what you were saying, right? I got the impression from what you were saying that you were not necessarily completely convinced that that there was not some level of uncertainty which you couldn't get below, as it were.
Well, I mean, any scepticism I expressed was just the same point that Joe was making when he showed that table of parameters that are set in the semi-analytic model. And by the way, there's many more pages than that.
Yeah, exactly.
So, there's a concern that, I mean, obviously many of these parameters are degenerate in practice, if not in physics, because the only thing that saves us, I guess, is that we take in a lot of, and it's been true in these studies as long as they've been going on, that the subgrid physics is an empirical description. I mean, you couldn't call it physics, but if you have a sufficiently complicated empirical description and enough empirical ingredients to constrain the parameters that go into it, then you can start to make predictions.
Right.
I mean, and it doesn't have to be correct at the level of Schrodinger's equation. It just has to be effective at capturing whatever the universe is doing.
That's right.
A bit like a neural network, artificial neural network or something.
I suppose, yeah, because I mean, a neural net is just a complicated way of interpolating.
Yeah.
So, so in a sense, what we're trying to do, I think, is almost say, look, is there an irreducible set of observations of the universe of galaxies, like the stellar mass function, its evolution, that once you set a model that can account for that, other things, other observations can be correctly predicted. So then it's almost physics free. It's just a question of how the
But we know from
things that we can see relate to each other. But I'm
so
not sure
of
we're
course
there
the
yet.
problem comes if you get different models matching the observations. Right. You can get a wrong model match the observations easily.
With the new generation of telescopes about to come in the next decade or so, will we be able to make a lot of progress in the star formation area, do you think? You'll see
Roger, why
much
don't you
more-
answer? You're the
Well, I think
observer.
you're going to have to wait, actually, because ALMA is there and has already shown us at least some of the mechanisms by which disks around stars evolved to make planets, for example. And ALMA, at least when that picture was produced, still wasn't looking at full capacity, and it's only just about there now. And so I think there's a huge amount that will come from ALMA in imaging star-forming regions. That's probably its main application, actually. And so I think it will be ALMA will be feeding your simulations with results at a really high rate. Because both the sensitivity and the resolution are just immensely higher than anything that's gone before.
And the JWST as well.
JWST will also play a big role here, but my guess would be that because of even for JWST, because of the dust,
No,
you'd be better off with that.
if you want something that's, if you like, taking you down in resolution, sure, it's ALMA. I mean, JWST will tell us what happened in the universe at early times,
Yeah.
which
The other side.
which is a kind of, it's a constraint, it's an observable that these calculations have to reproduce, but it doesn't directly bear on the physics that you inject.
Mark.
So I guess that's my comment. Like the other, so Alan's getting you the high resolution, so you can see where these things are happening. But the other side is for JWST is seeing things that happen at the earliest. That's where you calculate the bigger lever